Hello everyone. In this video we are going to make a simple Spur gear in SolidWorks, something that some of you asked me to make. I have made one under my playlist CAD with CATIA, but here we want to do the same thing in SolidWorks. So we need to define the major parameters for the gear, which are the number of teeth, the gear modulus, or the diametral pitch, and then you also have the pressure angle. So the first thing is we go under tools and we add our global variables. So we have the number of teeth, let's say 32. Then we have the gear modulus M, which is basically the diameter of the pitch circle over the number of teeth here. So here, if we assume that the diameter is like 4 inches for pitch circle, then this is going to be 4 divided by 32, or 1/8, which is 0.125. The unit of that is inch over number of teeth, which is the same as inches. And then we, of course, the pressure angle here, let's call it phi, and let's say that is 20 degrees. Okay, so these are the major parameters. There are some other parameters that we can add as well, but many of the dimensions for a gear they're mostly going to be calculated based on these parameters. For example, the pitch diameter PD can be calculated by basically M, the gear modulus, times N, the number of teeth, and you see it is going to be 4 inches, right? Or for example, the base circle diameter BD, it is equal to basically PD, right, times cosine of, and here you need the pressure angle. Okay, and you see the unit, it says in degrees, which is not correct. So here I have to add some inches. Let's see if it works. Oh, it's not gonna take it from me. So times 1 inches. There we go. So now let's reevaluate this. PD times cosine of phi, because PD now has units of inches. So if I go cosine of phi, let's see, now it's still showing as degrees, so I need to add probably times 1 inches. There we go. So make sure the dimensions are consistent and they are in inches. So this is the pitch circle, this is the base circle diameter, and then we need to add some other relations here, right? Like what? Like, for example, we need the external circle diameter or addendum. We need the root circle diameter or dedendum. And let me add those as well. So the addendum circle OD is basically equal to the pitch circle diameter plus, and it is going to be 2 inches divided by P, or 2 inches times M. So it's going to be 2 times M. And let's make sure, yeah, that's the addendum circle, the dedendum circle. We can call it the inner diameter, right? Let's call it DD. And this DD is equal to, again, the pitch circle diameter minus, and this is going to be 2.5 times M. So it's going to be this M times 2.5. So this is the addendum circle, that's the dedendum circle. Let me use AD instead of OD. That makes more sense to me. And then we also need a clearance, CL, which is going to be 0.25 times M. So I need to add that as well here, times 0.25. That is the amount of clearance that I need. Okay, so far these are some important parameters that I have calculated. And now you see they're all under the equations tab under the tree, and I can always right click manage equations and go back and modify anything that I need. So now the important thing is the involute curve, which is the profile of the tooth of the gear from base circle all the way to the addendum circle. We need to create that, and I have shown it in my other videos. It's a parametric design, and let me show it as well here. So this is the equation for it. If you want to draw it in XY plane, then it's going to be replaced by X and Y, but basically your horizontal coordinate is R of base sine t minus t cosine t. Your vertical one is R base times cosine t plus t sine t, and then you can change t from 0 to 2 pi. Basically, these are this is the tutorial I had for CATIA, right? And you can change it, and you can go basically from 0 to 2 pi. So you can create all of the points for the involutes, which you can see here, and then you can connect them with a spline. Now this is how you do it in CATIA. In SolidWorks, instead of creating these points using the functions and then connecting with the splines, there is the equation driven curve that you can basically apply. So here I go on the front plane, and then I draw the major circles. So the largest one is this guy, and the diameter for this is equal to the diameter of the addendum circle. Okay, this is your biggest circle. The next circle that is a physical circle is the circle with the smallest diameter, and that's the dedendum or the root circle. So this guy equals to the dedendum circle. And then we have other circles. One of them is the pit circle, and this one I make it a construction element because it's not real, it's an imaginary circle. And the diameter of this is equal to the pit circle. And finally, we have the base circle. Base circle is also imaginary. It's where the involute curve starts, and this guy also I make it for construction, and I provide the diameter for this as the base circle. Okay, so this is what I have for the major circles. Now what I need is I go here under a spline and use the equation driven curve. And here you can do explicit or parametric. Ours is parametric, so we use that. And the time here is changing from 0 to 2 pi, and in SolidWorks pi is an actual variable just like MATLAB. So you do not really need to type in 3.14 or something. And here the horizontal variable, as I showed you, is equal to 0.5 times diameter of the base circle. Now let's see if it recognizes diameter of the base circle times, and it is going to be sine of t and then minus t times cosine of t. Okay, and then we have something similar for the vertical coordinate, and you see it right away. It is going to give me a red thing because in this area it is not going to recognize that dB. So I need to, unfortunately, here type in the value for the base diameter, and that number is, as you saw it, this is 3.76. So I have to type in 3.76 here, and we'll see if this one is going to be okay. Yes, you see it's not picking on us here. And this one is R of base, which is half of the base diameter times cosine of t plus t times sine of t. Okay, and hopefully this one will give us an involute curve. And you see that is the involute curve, right? Now, of course, this is a what? This is a giant involute curve, right? And remember, if I go back to my equation-driven curve, this one, right? When t is 0, right? When t is 0, sine t minus t cosine t is going to be all 0, and then cosine t plus t sine t is going to be 1. So x is going to be 0, y is going to be what? Diameter of the base circle, and that is exactly this point here. You see, it is exactly starting on the base circle, and then when it goes to 2 pi, it goes one full revolution and comes back. So all I need is this portion of the profile, which is from here to what? To the addendum circle. The rest of it is not needed. So ideally, really, I do not need to go to 2 pi. I need an angle far less than that. So probably even if I go pi over 2, that is going to be still too much, right? Let's take a look here. You see, it's still too much. So if you want, you can further reduce the angle, although you can later trim it, right? It's not a big deal. You can always go ahead and trim this line, right? But you clearly see that you have a lot of redundancy here, and pi over 4, I would say, is much more reasonable. So this is the involute curve that you need. Now, the next thing you need to rotate this about the origin, some angle, to bring it to the left side of this vertical axis here. And then you need to mirror that. So you can create the left and the right side profile, and then you can trim it and make the profile of the first tooth. So I need to rotate this, but the question is, what is the rotation angle? How much is it that you need to what? You need to rotate it. And again, if you go and look at the equations that I provided in that CATIA lecture, this angle is going to be tangent of the pressure angle minus the pressure angle plus pi over 2n, where n is the number of teeth. So let's see if I can basically type in a formula for that. So the first thing is, or I can first go ahead and calculate it here. I can go here and calculate this. So here I call this maybe an angle, or let's call it theta, for example. This theta equals what? Equals, as I said, the pressure angle, but the important thing is since we are subtracting tangent of angle minus angle, the angle here has to be in radians, okay? Because tangent of the angle is going to be a number, but the angle here is in degrees. So what I need is, let me use the tangent function. So it's going to be the tangent of the pressure angle, right? Now, minus angle here, you have to convert your angle into what? You have to convert this phi into radians. And for that, I need to basically multiply it by pi, then divide it by 180. Okay, otherwise it's not going to work, because I need it in radians. And then you need to add to it pi over 2 divided by n. So it's going to be pi over 2, the whole thing, divided by n. Okay, and let's see. Here, it finds the whole thing, okay, in radians. That's the angle in radians. If you want, you can convert now this whole thing into degrees, right? So what I can do is grab this very whole thing, right? Then multiply it by 180 and divide it by pi. And the unit is going to be in degrees. Yeah, so I have to multiply it by 180 degrees divided by pi. So the angle is 3.66 degrees or 3.67 degrees. That's the angle that I need to rotate. So that's the angle in front of half of the tooth, the central angle. So let's see if we can go ahead and rotate this entity. So here we say rotate entity, and then we choose this guy. And for the center of rotation, of course, we choose origin. And then the angle here, let's see if it allows me to type a formula. It doesn't, so I have to type in the number. So here I type it, and let's see. There we go. You see, it rotated it 3.66 degrees. So now I can do a mirror here. And for that, I need to use the mirror entity and mirror this guy with respect to this line. And now I have the profiles that I need. All I need to do is to do a trimming. Okay, so I choose my trim tool, and then I trim the portions of this that I do not need. And now you see here is the profile of the tooth, as you can see, and I can get rid of this portion. So now my profile of the tooth, the involute, is completely done. The next thing I need to do is to connect this portion to what? To the root circle, and this portion does not necessarily have to be what? Involute again, because this portion is basically not going to have any connection whatsoever with your the other tooth, right? There is no connection here. So what I can do is I can connect with the line. One line goes to there, and then another line I go to here like that. And then I need to apply a fillet here. So I click on the fillet tool, and the fillet here should be equal to the clearance. And you see again, it is not going to let me type in the number, type in the formula for it. So I need to look at the CL, and that is 3125, 0.03125. So this is the number I need. And I need to apply it between here and here if it allows to. And it's not super happy, so let me first do a trimming, then see how we can possibly do a fillet. So now what? Here and here. Yeah, it's not necessarily allowing me to perform a fillet here, but I can do it later when I go to part design. But here, what you clearly can see, I have the profile of the tooth of the gear, right? I clearly have that. And one thing I can do is I can go ahead and I can trim this part and this part, or yeah, that's good enough actually for me. So let me go ahead and get this guy and then extrude it. The other parameter that you need is width of the tooth, and that can be a separate parameter that you can add here, right? So if you want, you can go here, and here, let's say I add another parameter, and this time I say this is equal to maybe 1/2 inch or something, right? That's the width of the gear. And then so here, when I choose this sketch and I extrude it, I choose the amount of extrusion to be equal to W. Okay, and if you want, you can make it to be symmetric as well, right? But I guess this is good enough now. So the other thing you need is you go on the front plane and you draw your base circle, right? So you draw a circle that goes from here to there, and the diameter of this should definitely be equal to the diameter of the base circle. And or the root circle in this case, actually. So let me change this. This should be equal to the diameter of the root circle. So let's see, the dedendum circle. which is touching this guy basically. Yes. And here we go, and now I should be able to extrude this as well, equal to the width of the gear, right? And now I have the gear, as you can see. So now I can do a circular pattern. So now I make the axis visible, and then I get this guy, right, this bus extrude, and then go to pattern, and then I do a circular pattern here. And so it's going to be about this, and the number of teeth is going to be equal to n, and this should be equal spacing, sorry, here. Let's see, instant spacing, 32, right? I don't think it's going to do it, but let's see. Yeah, no, it did. Good. So 32. So now here, that's my gear with 32 teeth. And what I need to do is to create a hole here and provide the diameter of the shaft. So I can add one more thing here, and that is the shaft diameter. And let's say in this case, it is, let's say, an inch, right? And here I go and create my circle and provide the diameter. And then I need to add a keyway if I want to. So here, let's see if I can add a keyway like this. Then you can trim it, right? So okay, so this is what you have, and you can provide again dimensions here. So let's say this is equal to 1/3 of the shaft diameter, right? And then you can provide some height as well. And let's say this is equal to shaft diameter over 8. Okay, so now you have this, and you're going to cut extrude it through all, and you get your beautiful gear. And let's go ahead and apply some material. One of my favorite material is copper, which has a beautiful color, and I guess this is a simple Spur gear. And now you can go ahead and change everything, right? So if you want to change everything, the only places that you have to be careful, that you have to manually modify, is one of them is that amount of rotation that you did, that rotation angle with angle theta, you did it manually, it didn't accept it. In the involute curve also, it did not necessarily do a beautiful job, because it did not take the radius of the base for me in that equation driven curve. So there are a few places that the window did not allow you to insert parameters. Although we put them in double quotation mark, it didn't allow me. I look for solutions for that. If I find the solution, I'll let you know in my future videos. But basically, this is what you have over here, and hopefully this is a relevant video for you on how to make a Spur gear in SolidWorks. Thank you so much for your attention. I will see you in my next video.